This video is for those of you who are studying for the physics final exam. This particular video contains topics on thermolinear expansion, gas laws, heat transfer problems like specific heat problems, latent heat, calorimetry, thermodynamics, heat engines, and entropy. So just to give you an idea of the content that will be in this particular video. So let's go ahead and start with this problem. Number 1, a 300-meter long rod of iron at 20 degrees Celsius has a coefficient of linear expansion of 12 times 10 to the minus 6 Celsius to the minus 1. What will be the length of the rod at 50 degrees Celsius? So let's draw a picture. Let's say this is the rod. It's 300 meters long. So that's the length. What happens to the length when you raise the temperature? The length is going to increase. Whenever you heat a metal or a solid, the solid will expand, but not by much though. But it's proportional to temperature. But how can we calculate the new length? What equation do we need? We need to use this formula. The change in length is equal to alpha, that's the coefficient of linear expansion, times L0, which is the original length of the rod, times delta T. This is the change in temperature, which could be in Celsius or in Kelvin. Now, alpha, we're told that it's this number, 12 times 10 to the minus 6 Celsius to the minus 1. L0 is 300 meters. Now, the change in temperature, the final temperature is 50. The initial temperature is 20 degrees Celsius. So that's a change of 30. So 12 times 10 to the minus 6 times 300 times 30 gives us a change in length of 0.108 meters. Now we're looking for the current length at this temperature. So that's going to be the original length plus the amount that the rod changed, or the change in length. So that's going to be 300 plus 0.108 meters. So the final answer is 300.108. So that's going to be the new length of the rod. Number 2, a 50 milliliter sample of pure ethanol rests in a 100 milliliter container at 15 degrees Celsius. The coefficient of volume expansion of ethanol is 1100 times 10 to the minus 6, and the units should be the same, Celsius to the minus 1. What will the volume of ethanol in the container be at 70 degrees Celsius? So here's the formula that we need. The change in volume is equal to beta. This is the coefficient of volume expansion times the original volume times delta T. So let's draw a picture. So let's say this is the ethanol in a container. As we raise the temperature, the volume will increase. The liquid will expand. So we need to calculate the new volume. So first, let's calculate the change in volume. So beta is 1100 times 10 to the minus 6. The original volume is 50 milliliters. And the change in temperature, that's going to be the difference between 70 and 15 degrees Celsius. 70 minus 15 is 55. So it's going to be 55 times 50 times 1100 times 10 to the minus 6. And so the change in volume is 3.025 milliliters. Now let's calculate the new volume, which will be the original volume plus the change in volume. So it's simply 50 plus 3.025. So it's now 53.025 milliliters. So that's going to be the new volume of ethanol when we raise the temperature from 15 degrees Celsius to 70. So as you can see, whenever you raise the temperature of a fluid, the volume of the fluid will increase. The liquid is going to expand. Number 3, the pressure of gas inside a 3-liter container is 8 atm. What will the new pressure be if the volume of the container doubles to 6 liters? Let's draw a picture. So let's say this right here is the 3-liter container. Now let's put some gas molecules inside this container. Now let's draw a much larger container. Let's say this is the 6-liter container. Now let's put the same number of gas molecules in this container. Which one will have the higher pressure? The one on the left or the one on the right? So the one on the left will have a higher pressure. The pressure exerted by a gas is proportional to the number of collisions between the gas molecules and the walls of the container. So on the left, because there's less space, the molecules will collide with the container more frequently. On the right side, there's more space. So as a result, the gas molecules will collide with the walls of the container less frequently. But here it's going to be more frequently. And so that's why the pressure is higher when the volume of the container is lower. So thus we have Boyles Law, which shows the relationship between the volume of a gas and the pressure. The volume of the gas is going to be the same as the container. This is going to be an inverse relationship, which means that as you increase the volume, the pressure decreases proportionally. So right now, we've increased the volume by a factor of 2. So the pressure will decrease by a factor of 2. So if we divide 8 by 2, we should get the new pressure, which will be 4. Now, we can confirm this with an equation. The equation associated with Boyles Law is P1V1 is equal to P2V2. So now let's do the math. P1 is 8 atm. V1 is 3 liters. We're looking for P2. V2 is 6 liters. So in order to solve for P2, we need to divide both sides by 6 liters. 3 divided by 6 is basically a half, or 0.5. And the unit liters will cancel. So it's going to be 8 atm times 0.5, and half of 8 is 4. So that's another way in which you can get the answer. So the new pressure is going to be 4 atm. So make sure you understand that concept. As the volume of a gas increases, the pressure decreases. Number 4. The pressure inside a tire is 215 kilopascals at 12 degrees Celsius. What will the tire pressure be at 32 degrees Celsius? So if we raise the temperature of a gas, what's going to happen to the pressure? Will it increase or decrease? What would you say? Let's draw a picture again with a few gas molecules inside a container. As we raise the temperature, the kinetic energy of the gas molecules will increase. Now, kinetic energy depends on 2 things, mass and speed. As we raise the temperature, the mass of the particles will not change, so the speed will increase. And as the speed increases, the number of collisions that the gas molecules make with the walls of the container will increase, and this will lead to an increase in pressure. So increase in the temperature will cause an increase in pressure. Now, what formula should we use? Perhaps you've seen this equation, the combined gas law. Notice that if temperature is constant, we'll get the equation that we used in the previous example, which was associated with Boyles Law. But in this example, volume is constant. So we get the formula P1 over T1 is equal to P2 over T2. P1 is 215 kilopascals. We're looking for P2. Now what's T1 and T2? You don't want to plug in 12 degrees Celsius for T1. When dealing with this equation, or the combined gas law equation, the temperature has to be in Kelvin. To calculate the Kelvin temperature from the Celsius temperature, it's basically 273.15 plus the Celsius temperature. But just to keep things simple, let's round it to 273. So 12 plus 273, that's going to be 285. So that's T1 in Kelvin. T2 is going to be 32 plus 273, and so that's going to be 305 Kelvin. In order to solve for P2, we need to cross multiply. So we're going to have 285 Kelvin times P2, that's this part, and that's equal to 215 kilopascals times 305 Kelvin. And I'm running out of space. Now let's divide both sides by 285 Kelvin. So as we can see, the units Kelvin will cancel, giving us the answer in kilopascals. So it's going to be 215 times 305 divided by 285. So the new pressure, P2, is 230.1 kilopascals. And so that's it for this problem. Number 5. A 4 cubic meter container at 300 Kelvin has a gas pressure of 250 kilopascals. If the temperature triples to 900 Kelvin and the volume is reduced by half to 2 cubic meters, what will the new gas pressure inside the container be? Now, before we use a formula to get the answer, let's see if we can get the answer conceptually. So right now, P1 is 250 pascals. We want to calculate the new gas pressure when the temperature and the volume changes. So let's focus on temperature first. The temperature increases from 300 Kelvin to 900 Kelvin. So it increases by a factor of 3. Now let's talk about the volume. The volume initially is 4 cubic meters, and then it goes down to 2 cubic meters. So it reduces by a factor of 2. Now we know that when the temperature goes up, the pressure goes up. So because the temperature increased by a factor of 3, the pressure will increase by a factor of 3. Now, when the volume goes down, the pressure will go up because they're inversely related. So because the volume decreased by a factor of 2, the pressure will increase by a factor of 3. So 3 times 2 is 6. So the pressure, which was 250 kilopascals, is going to increase by a factor of 6. So the new pressure should be 1500. Now let's confirm this with an equation. So it should be 1500 kilopascals. Now let's use a formula to get the answer. P1 V1 over T1 is equal to P2 V2 divided by T2, the combined gas law equation. V1 is 4 cubic meters. T1 is 300 Kelvin. We're looking for P2. V2 is 2 cubic meters, and T2 is 900 Kelvin. So let's plug in everything. So this is going to be 250 times V1, which is 4, over T1, that's 300 Kelvin, equals P2 times V2 over T2. So let's cross multiply. Here we have 300 times 2 times P2. So that's going to be 600 P2. Here we have 250 times 4, that's 1000, and then times 900. So let's divide both sides by 600. 600 divided by 900, we can cancel 2 zeros, so it becomes 9 over 6. So we have 1,000, and 9 is basically 3 times 3. 6 is 3 times 2. So we could cancel a 3. Now 1,000 divided by 2 is 500. So this becomes 500 times 3. 5 times 3 is 15. Add in the 2 zeros, we get 1,500 kilopascals. So this right here is the answer. That's the new pressure inside this container. Number 6. An 8-liter storage tank is filled with nitrogen gas at STP. What is the mass of nitrogen in kilograms that is stored in the tank? We're going to use this equation. PV is equal to nRT. It's the ideal gas law equation. But what is STP? STP stands for standard temperature and pressure. The standard temperature is 273 Kelvin. The standard pressure is 1 atm. Now, it's important to understand that 1 atm is equal to 1.013 times 10 to the 5 pascals, which is 101.3 kilopascals. And it's also equal to 760 torr. Now keep in mind 1 pascal is equal to 1 Newton of force exerted over 1 square meter. Pressure is force over area. Now what unit should the pressure be in? Should we use units of atm or pascals? It really depends on the R value that you choose to use. Now, if you use this R value, 0.08206, the volume has to be in liters, the pressure has to be in atm, N is going to be in moles, the temperature will be in Kelvin. The other R value that you could use is this one, 8.3145 joules per mole per Kelvin. If you're going to use this R value, pressure has to be in pascals, and the volume has to be in cubic meters. Now keep in mind 1 cubic meter is equal to 1,000 liters in the event that you need to convert from liters to cubic meters. But because we have the pressure in atm and we have the volume in liters, we're going to use the first R value, 0.08206. So let's plug everything that we have into this equation. Our goal is to calculate N. Once we have N, the number of moles, we can convert that into grams and then convert that into kilograms. So P is 1 atm, the volume is 8 liters, R is 0.08206, and T is 273. So let's begin by multiplying 0.0826 by 273. So this is going to be 22.40238. And then let's divide both sides by that number. So N is going to be 8 divided by that number. So the number of moles is 0.357. Now the next thing that we'll need to do is use the periodic table to calculate the molar mass of nitrogen gas. The chemical formula for nitrogen gas is N2, and the atomic mass of a nitrogen atom is 14.01. So multiply that by 2, the molecular mass is going to be 28.02. Now, you can leave this as 28.02 atomic mass units, or you could use the units grams per mole, which is what we're going to use. So that's the molar mass of N2. So let's start with the number of moles of N2. Keep in mind, for those of you who are not sure of what a mole is, think of a dozen. A dozen represents 12. A dozen is a quantity. A mole is also a quantity. a mole is just 6.022 times 10 to the 23. It represents a large quantity of something. Now let's convert from moles to grams. So 1 mole of N2 has a mass of 28.02 grams. You want to set it up in such a way that the unit moles will cancel. Next, let's convert grams to kilograms. 1 kilogram is equal to a mass of 1,000 grams. So now the unit grams cancel. So it's going to be 0.357 times 28.02 divided by 1,000. And so the answer for part A is 0.01 kilograms of nitrogen. So that's the mass of nitrogen that is in this 8-liter storage tank at STP. Now let's move on to part B. What is the density of nitrogen gas at STP? So we know that density is mass over volume, but we really don't need to use the formula. We can convert it to get the answer. Now this mass could be in grams and the volume could be in liters, or it could be in kilograms and the volume could be in cubic meters. So these are some common ways in which we can calculate the density of a gas. So let's get it in both of these units. Let's start with the molar mass of nitrogen. We said it was 28.02 grams per mole. Now, at STP, you need to know that 1 mole of gas occupies a volume of 22.4 liters. So we could say 1 mole over 22.4 liters in the next step. Notice that the unit moles will cancel, giving us grams per liter. So this will give us the gas density if you take the molar mass and divide it by 22.4 at STP. So the gas density of nitrogen gas is 1.25089, or we could just round that to 0.9 grams per liter. Now let's convert this answer to kilograms per cubic meter. Now let's convert grams to kilograms. 1 kilogram is equal to 1,000 grams. So the unit grams cancel. And let's convert liters to cubic meters. There's 1,000 liters per cubic meter. So now the unit liters cancel. And so we're left with kilograms per cubic meter. Now also the number 1,000 cancels as well. So the answer doesn't change. It's 1.2509 kilograms per cubic meter. So that's the density of nitrogen gas at STP. Number 7. How many molecules are present in a 1 liter sample of oxygen gas at STP? So what do you think we need to do in this problem? Well, let's start with what we're given, which is 1 liter. Now recall that at STP, 1 mole of gas occupies a volume of 22.4 liters. So we can convert from liters to moles. So let's put liters on the bottom so that these units will cancel, and 1 mole on top. Now, how can we convert from moles to molecules? You need to be familiar with Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23. And since we're dealing with 1 liter of oxygen gas, O2 is a molecule. So right now we have moles of O2. So 1 mole of O2 is equal to 6.02 times 10 to the 23 molecules of O2. So the unit moles will cancel. So now let's do the math. It's going to be 1 divided by 22.4 times Avogadro's number of 6.02 times 10 to the 23. And so you should get this answer, 2.6875 times 10 to the 22 molecules. So that's it. Number 8. What is the average translational kinetic energy of molecules in a gas at 27 degrees Celsius? The average translational energy is going to be 3/2 times Boltzmann constant times the temperature in Kelvin. Boltzmann's constant is equal to 1.38 times 10 raised to the negative 23 joules per Kelvin. Now, we need to get the Kelvin temperature. So it's 27 degrees Celsius plus 273, which is going to be 300 Kelvin. So it's going to be 3 times 1.38 times 10 to the minus 23 times 300 divided by 2. And so the average translational kinetic energy of the gas molecules at 27 degrees Celsius is 6.21 times 10 to the negative 21 joules. As we can see here, the units Kelvin cancel, giving us the unit joules. Number 9. What is the RMS speed, or the root mean square speed, of nitrogen molecules in the air at 100 degrees Celsius? The equation that we could use to find the root mean square velocity is the square root of 3 RT divided by the molar mass of the gas molecule in kilograms per mole. Now, in order for this equation to work, you need to use the R value 8.3145 joules per mole per Kelvin. Now, the Kelvin temperature is going to be 273 plus the Celsius temperature, so that's 373 Kelvin. The molar mass of nitrogen gas was 28.02 grams per mole. We need to convert grams to kilograms in order for this to work. So 1 kilogram is 1,000 grams. And so this is going to be 28.02 divided by 1,000, which is 0.2802 kilograms per mole. So go ahead and plug this into your calculator. So you should get a root mean square velocity speed of 576.2 meters per second. So this right here is the answer. Now, I'm going to show you another thing that you can do to get the same answer. It's a similar formula, but it looks a little bit different. Instead of 3 RT, it's going to be 3 times Boltzmann's constant times the temperature. And instead of dividing by the molar mass, we're going to divide it by the mass in kilograms. So let's get the mass first. The atomic mass unit of N2 is 28.02. Now, instead of writing grams per mole, we're going to use atomic mass units. Now, 1 atomic mass unit is equivalent to 1.66 times 10 to the minus 27 kilograms. So a single N2 molecule has a mass of this number times that. And we're about to see what it is. So a single nitrogen gas molecule has a mass of 4.651 times 10 to the minus 26 kilograms. So now let's plug in everything. Boltzmann's constant, which we used before, that's 1.38 times 10 to the minus 23 joules per Kelvin. And the Kelvin temperature is still 373 Kelvin. And then let's use a mass of 4.651 times 10 to the minus 26. So go ahead and type that in. So this will give you the same answer of 576.2 meters per second. So you can use either one of these two formulas in order to calculate the RMS speed of a gas molecule. Number 10. Calculate the internal energy of 5 moles of helium at 400 Kelvin. Now, helium is a monoatomic gas. It has the chemical symbol He, and it's basically just one atom. Nitrogen gas is a diatomic gas because a single molecule of N2 consists of 2 atoms. Now, in order to calculate the internal energy of a monoatomic gas, the formula that we need is this. Capital U is the symbol for internal energy, and it's equal to 3/2 nRT. So N is the number of moles, that's 5 moles. R is going to be 8.3145 joules per mole per Kelvin. And the temperature is 400 Kelvin. So let's pay attention to the units. We can see that the unit Kelvin cancels, the unit moles cancel, giving us the unit joules. So it's 3 times 5 times 8.3145 times 400 divided by 2. And so the internal energy of this gas at 400 Kelvin is 24,943.5 joules. So as you can see, the internal energy of a gas is dependent on temperature. As the temperature increases, the internal energy increases. Now, for those of you who truly value this video, if you want to show your appreciation, one of the best ways you can do so is by subscribing to this channel. And it really doesn't take too long. Just click on that red button at the bottom of the screen, and that's it. By the way, if you decide to do so, don't forget to turn on or click on that notification bell. Now, for those of you who want to support my channel, here's the link to my Patreon page. Also, when you get a chance, check out the links in the description section below this video, because I'm going to post some other resources that you might find helpful. So let's get back to the video. Number 11. How much heat energy in kilojoules is needed to raise the temperature of 12 kilograms of water from 20 degrees Celsius to 35 degrees Celsius? And we're given the specific heat capacity of water. It's 4186 joules per Kelvin per Celsius. Now, what formula do we need in order to get the answer? Perhaps you've seen this equation. Q is equal to mc delta T, or Q equals mcat. Q is basically the amount of heat that's needed to raise the temperature from 20 to 35 degrees Celsius. M is going to be the mass in kilograms. C is the specific heat capacity, which is 4186 joules per kilogram per Celsius. The change in temperature is the final temperature of 35 minus the initial temperature of 20. So the unit Kelvin will cancel, and the unit Celsius will cancel. So 35 minus 20 is 15 times 12 times 4186. So Q is going to be 753,480 joules, as we can see here. Now we want the answer in kilojoules, so let's convert it. 1 kilojoule is equal to 1,000 joules. So we need to divide our answer by 1,000. So our final answer is going to be 753.48 kilojoules. So that's how much thermal energy is needed to heat 12 kilograms of water from 20 to 35 degrees Celsius. Number 12. 0.5 kilograms of water at 90 degrees Celsius is poured into an empty 3 kilogram aluminum container initially at 15 degrees Celsius. What will be the final temperature when the mixture reaches thermal equilibrium? So let's draw a picture. So let's say we have this aluminum container, and we're going to put some water in it. Now initially the water is at 90 degrees Celsius, and the container is at 15. So heat always flows from hot to cold. So heat is going to flow from the water to the surrounding container. Now, the temperature of the water is initially 90. As heat is released from the water, the temperature will decrease to some final thermal temperature. The temperature of the aluminum container is 15. As it absorbs thermal energy, the temperature will increase to TF. So when the rate at which heat leaves the water equals the rate at which heat is absorbed by the container, thermal equilibrium will be reached, and it's going to be at some final temperature. So when the temperature of water and the container is the same, that's going to be TF. That's when the system achieved a state of thermal equilibrium. But how can we calculate this final temperature? What do we need to do? Now, we need to understand that the quantity of heat energy that is released by the sample of water is equal to the quantity of heat absorbed by the aluminum container. So Q of water must equal Q of Al. Now, we need to put a negative sign on only one side of the equation in order for this to work. It really doesn't matter which side you put it, but as long as you put it there, it'll work. Now, based on the last problem, we know that Q is equal to mc delta T. So the mass of water is 0.5 kilograms. The specific heat capacity of water is 4186, as we can see here. And the change in temperature, it's going to be the final temperature of the system minus the initial temperature of the water, which is 90 degrees Celsius. The mass of aluminum that we're dealing with is 3 kilograms. The specific heat capacity of aluminum is 900. And delta T is going to be the final temperature minus the initial temperature of the aluminum container, which is 15 degrees Celsius. So first, let's multiply 0.5 by 4186. And so that's going to be negative 2093. 3 times 9 is 27, so 3 times 900 is 2700. Now let's distribute. So we're going to have negative 2093 TF, and then negative 2093 times negative 90, that's going to be positive 188,370. And that's going to equal 2700 TF, and then minus 2700 times 15, so that's 40,500. Now let's do some algebra. So let's add 2093 TF to both sides. And at the same time, let's add 40,500. So these will cancel. 188,370 plus 40,500. That's going to be 228,870. And 2,700 plus 2093, that's 4,793 times TF. So let's divide both sides by 4,793. So the final temperature at thermal equilibrium is going to be 47.75 degrees Celsius. And this answer makes sense because it's between 90 and 15 degrees Celsius. If we get an answer that is outside of that range, that is more than 90 or less than 15, we know it has to be wrong. So this answer is reasonable. Number 13. How much heat is required to melt 200 grams of ice? The latent heat of fusion of ice is 333 kilojoules per kilogram. Whenever there's a phase change, in this case, ice is melted into liquid water, to calculate the heat associated with such change, you could use this formula. It's basically the mass times the latent heat of fusion. Now, the latent heat of fusion doesn't have the unit grams, it has kilograms. So we need to convert grams to kilograms. So let's start with a mass of 200 grams. And let's convert that to kilograms. So 1 kilogram is 1,000 grams. So 200 divided by 1,000, we get a mass of 0.2 kilograms. And then we're going to multiply that by the latent heat of fusion, which is 333 kilojoules per kilogram. So now the unit kilograms will cancel, giving us the unit kilojoules. So it's 200 divided by 1,000, which is 0.2 times 333. So the thermal energy that's needed to melt 200 grams of ice is 66.6 kilojoules of heat energy. So that's it for number 13. Number 14. How much heat is required to heat 350 grams of ice at negative 18 degrees Celsius to liquid water at 42 degrees Celsius? The latent heat of fusion of ice is 333 kilojoules per kilogram. And we're also given the specific heat capacities of ice and water. Let's begin with a number line. So the initial temperature we're starting with is negative 18 degrees Celsius. And we need to raise it to 42. Now, water melts at 0 degrees, ice melts at 0 degrees Celsius. So this is ice, and this is going to be liquid water on the right side. Now, we need to break this problem into 3 parts. Q1 will represent the energy that's needed to heat ice from negative 18 degrees Celsius to 0. Q2 is going to be the heat energy that's needed to melt ice into liquid water. Q3 will be the thermal energy that's needed to heat liquid water from 0 to 42. Q would represent the total heat required, which is going to be the sum of the 3 smaller Q values. So let's begin by calculating Q1. So it's a temperature change problem. We're going from negative 18 degrees Celsius to 0. So we need to use this formula, MC delta T. So the mass of ice is 350 grams. If we convert that to kilograms by dividing by 1,000, that's going to be 0.35 kilograms. The specific heat capacity for ice is 2100. The change in temperature, it's going to be the final temperature minus the initial temperature. So that's 0 minus negative 18. And so that's just going to be positive 18. So 18 times 2100 times 0.35, that's going to be 13,230 joules. Now let's divide that by 1,000 to convert it to kilojoules. So Q1 is 13.23 kilojoules. Now let's calculate Q2. So we need to use this formula. It's going to be M times L. So M is the mass in kilograms, 0.35. L is the latent heat of fusion, which is 333 kilojoules per kilogram. So I'm going to write the units though, so you can see what units we get. And so you can see that the units kilogram will cancel. And so we're going to get the units in kilojoules. So Q2 is 116.55 kilojoules. So now we need to calculate Q3. So that's a temperature change problem. We're going to use this formula again. So the mass is still going to be 0.35 kilograms. The specific heat capacity of water is 4186. This is joules over kilograms times Celsius. And the change in temperature, we're going from 0 to 42. So that's a change of 42 degrees Celsius. So the unit Celsius will cancel and kilograms will cancel, giving us the unit in joules. So 0.35 times 4186 times 42 is 61,534.2 joules. Now, if we divide that by 1,000, this is going to be 61.53 kilojoules. So now we can calculate the total heat that's required to heat 350 grams of ice from negative 18 degrees Celsius to liquid water at 42. So we need to add up Q1, Q2, and Q3. So this is going to be 191.31 kilojoules. So this is the final answer for this problem. Number 15. Calculate the rate of heat flow through a 0.5 meter long cylindrical rod of copper metal with a cross-sectional area of 0.10 square meters if the temperature across this rod are 15 and 28 degrees Celsius. So let's begin with a picture. So on the right side, we're going to say that this part is the hot portion, and the left side is hot, and let's say the right side is cold. So the temperature on the left side, we're going to say it's 28 degrees Celsius. On the right side is 15. Heat is going to flow from hot to cold. Now, the copper metal bar, or rather the copper rod, I should say, it's 0.5 meters long. And the cross-sectional area of the rod is 0.10 square meters. How can we find the rate at which heat will flow from one end of the rod to the other? We know heat is Q, but the rate at which it flows is the change in Q divided by the change in time. That's equal to the thermal conductivity of copper times the cross-sectional area times the temperature difference divided by the length of the rod. The thermal conductivity of copper, that's 420 joules per second per meter per Celsius. The cross-sectional area is 0.10 square meters, but I'm going to write it as meters times meters. And the temperature difference is 28 minus 15, so that's 13 degrees Celsius, divided by the length of the rod, which is 0.5 meters. Now let's pay attention to the units. We can cancel meters, we can cancel another pair of meters, and we can cancel Celsius. So the units that we have left over is joules per second. So it's 420 times 0.10 times 13 divided by 0.5. So the answer is 1092 joules per second. 1 joule per second is equal to 1 watt, and watts represents the unit of power. So power is the rate at which energy flows. So we could say that this is 1092 watts. That's it for this problem. Number 16. How much power is released by a spherical metal ball with a radius of 40 centimeters at 350 Kelvin. So let's draw a picture. So here we have a ball at 350 Kelvin, and it's going to emit thermal radiation. Every object emits thermal radiation. But how much radiation is released? Power is going to equal the change in the thermal energy divided by the change in time. As we talked about earlier, is the rate at which energy flows. Now, the formula that we're going to use is a little bit different. It's going to equal the emissivity of the spherical metal ball times the Stefan-Boltzmann constant times the surface area of the sphere times the temperature raised to the fourth power. Now we have the emissivity ratio, which is 0.32. The Stefan-Boltzmann constant, that's 5.67 times 10 to the minus 8 watts per square meter times Kelvin to the fourth power. And you could find that number in your textbook. It's basically just a constant. Now, the area or surface area of a sphere is going to be 4 pi r squared. So that's 4 pi, and 40 centimeters, if you divide that by 100, that's 0.4 meters. So 4 pi times 0.4 squared, that's going to be, I'm going to write that here, 2.01 square meters. And then let's multiply this by 350 Kelvin raised to the fourth power. So now let's pay attention to the units. The unit square meters will cancel, and the units Kelvin to the fourth power will cancel, giving us the power in watts. So it's going to be 0.32 times 5.67 times 10 to the minus 8 times 2.01 times 350 raised to the fourth power. And you should get 547.3 watts, or 547.3 joules per second. So that's the answer. Number 17, 1200 joules of work is done on the system and 800 joules of heat is released from the system. What is the change in the internal energy of the system? So now we're moving into thermodynamics. According to the first law of thermodynamics, the change in the internal energy of the system, represented by delta U, is equal to Q minus W. Q represents the amount of heat that either enters or leaves the system. If heat flows into the system, Q is positive. If heat is released by the system, Q is negative. W is the work done on or by the system. Now, W is positive if the work is done by the system. W is negative if the work is done on the system. So these are some things that you want to keep in mind. So looking at part A, 1200 joules of work is done on a system. So what is W? Is W positive or negative 1200? As we said before, whenever work is done on a system, it's negative. So it's negative 1200. Now what about Q? We're told that 800 joules of heat is released from the system. Is Q positive 800 or negative 800? Because the system releases heat, it's going to be negative 800 joules. So delta U is going to be negative 800 minus negative 1200. And so we could change these two negative signs into a positive sign. So negative 800 plus 1200 is positive 400 joules. So this is the change in the internal energy of the system, which means that the internal energy of the system increased by 400 joules. Now, what about part B? Feel free to try that if you want to. What is the change in the internal energy of the system if 1500 joules of heat is added to it and 900 joules of work is done by the system? So what's Q in this example? Well, since we're adding heat, Q has to be positive 1500 joules. What about W? Work is done by the system. Whenever work is done by the system, W is positive. So it's going to be positive 900 joules. So delta U is going to be 1500 minus positive 900. So 1500 minus 900 is 600. So the internal energy of the system increases by 600 joules. So that's the answer for part B. Number 18. Which of the following represents a process where no heat transfer can take place into or out of the system? So let's go through each one. Is it an isochoric process? An isochoric process is a process that occurs at constant volume. The change in volume is 0. So on a pressure volume diagram or a PV diagram, this would be an isochoric process, either going up vertically or going down. So that would be an example of an isochoric process. Now let's talk about an isobaric process. Think of a barometer, which measures pressure. An isobaric process, iso means the same. So we're dealing with constant pressure. The change in pressure is 0. In a PV diagram, an isobaric process is one in which you're traveling horizontal in a PV diagram. It could be towards the right or towards the left. Now, what about an isothermal process? So think of thermal, think of temperature. So the temperature is constant. Delta T is 0. On a PV diagram, an isothermal process looks like this. So let's say we're going from A to B. The temperature is constant. Now for an adiabatic process, Q is 0, which means that no heat flows into or out of a system. The PV diagram for an adiabatic process looks very similar for an isothermal process. But this is the answer we're looking for. Q is 0 for that process. So D is the right answer. Number 19. How much work is done by the system when a gas expands from a volume of 10 liters to 30 liters at a constant pressure of 5 atm? And also, what is the name of this process? So go ahead and take a minute to work on that problem. Feel free to pause the video. Now, we have a process occurring at constant pressure. So we know that this is an isobaric process. How do we calculate the work done during an isobaric process? The formula is pressure times the change in volume. So the pressure is 5 atm. The change in volume is the final volume, which is 30 liters, minus the initial volume of 10 liters. So that's a change in 20 liters. 5 atm times 20 liters is 100 liters times atm. Now let's convert this to joules. 1 liter times 1 atm is equal to 101.3 joules. That's a conversion factor that you want to keep in mind. So it's going to be 100 times 101.3. So the work done by the gas as it expands is 10,130 joules. So whenever a gas expands, the work done is positive. Number 20. 1.5 moles of a gas expands adiabatically, causing the temperature to change from 1200 Kelvin to 400 Kelvin. Calculate the change in the internal energy of the system. So go ahead and try that problem. The change in the internal energy of the system is 3/2 nR delta T. So this is going to be 3/2. N is the number of moles, which is 1.5 moles. R is 8.3145 joules per mole per Kelvin. The final temperature is 400 Kelvin. The initial temperature is 1200 Kelvin. So 400 minus 1200, that's negative 800. times 8.3145 times 1.5 times 3/2. And you should get negative 14,966.1 joules. So that's the change in the internal energy of the system when the gas expands adiabatically. Now what about part B? How much work is done by the gas during this process? We know that delta U is Q minus W, according to the first law of thermodynamics. Now, for an adiabatic process, what do we know? This is a process where no heat can be transferred into or out of the system. So, for an adiabatic process, Q is 0, which means delta U is equal to negative W, or W is negative delta U. So the work done is going to be negative times negative 14,966.1. So the work done by this gas is positive 14,966.1 joules. 21. 1,600 joules of heat energy is added to the system during an isochoric process. How much work is done during this process? So if you recall, an isochoric process is a process that occurs at constant volume. So the change in volume is 0. Now what you need to know is that the work done during an isochoric process is 0. So that's the answer for part A. Now what about part B? The change in the internal energy of the system is Q minus W. Since W is 0, the change in the internal energy of the system is just Q. And Q is the 1,600 joules of heat energy that was added to the system. So delta U is 1,600 in this problem. So that's all we need to do for number 21. Now for those of you who want more example problems on thermodynamics, particularly those with PV diagrams, I'm going to post some links in the description section below in this video. So feel free to take a look at that when you get a chance. Let's move on to this question. 5 moles of an ideal gas expands from a volume of 4 cubic meters to 10 cubic meters at 350 Kelvin during an isothermal process. How much work is done by the gas? The work done by a gas during an isothermal process, it's equal to nRT times the natural log of the final volume divided by the initial volume. So N is 5 moles, R is 8.3145 joules per mole per Kelvin, the temperature is 350 Kelvin, the final volume is 10 cubic meters, the initial volume is 4 cubic meters. So let's go ahead and plug this in. So you should get W is equal to positive 13,332 joules. So that's how you can calculate the work done during an isothermal expansion. Now, what about part B? What is the change in the internal energy of the system? Delta U is equal to 3/2 nR delta T. Now, during an isothermal process, delta T is 0, so delta U has to be 0. So this is the answer for part B. Now what about part C? Delta U is equal to Q minus W. So if delta U is 0, if we add W to both sides, we can see that W is equal to Q. So Q is going to be the same as this answer, positive 13,332 joules. So that's the answer for part C. Number 23. A heat engine produces 7,500 joules of heat at 600 Kelvin while releasing 6,000 joules of heat energy to the environment at 300 Kelvin. Calculate the amount of useful work that can be performed by this engine. So let's draw a simple diagram that represents this heat engine. So at the top, we have the temperature of basically the hot reservoir of the heat engine. And at the bottom, basically this is the temperature of the environment, which is 300 Kelvin. So that's like the cold section. Now, heat flows from hot to cold. So the heat engine generates 7,500 joules of thermal energy. So this is QH. And then out of that 7,500, 6,000 joules of heat energy is released to the environment. So that's QC. Now the difference between QH and QC is the amount of useful work that the engine will perform. So this engine, this heat engine, takes a portion of the heat energy generated and converts it into useful mechanical work. So it's going to be QH minus QC, or 7,500 minus 6,000. So the amount of useful work that can be performed by this engine is 1,500 joules. Now let's calculate the efficiency. This is part B. The efficiency is basically the mechanical work divided by QH. So that's 1,500 joules divided by 7,500 joules. And so this comes out to be 0.2, which means that it's 20% efficient. So 20% of the heat energy generated by this device is converted to work. The other 80% is discarded as waste energy. So this is the 80% of the energy that's lost to the environment, but 20% has been converted into useful work. So that's what the efficiency tells us. How much of the total energy that was generated was converted to work. Now let's move on to part C. What is the maximum Carnot efficiency of this engine based on the operating temperatures? We could use this formula to calculate the maximum efficiency. It's TH minus TL over TH. And if you're going to use this formula, the temperature has to be in Kelvin, not Celsius. So TH is 600 Kelvin, TL is 300 Kelvin, divided by 600. 600 minus 300 is 300. So it's 300 over 600, which is 0.50 or 50%. So the maximum efficiency that we can get for this particular heat engine based on the operating temperatures is 50%. Right now the engine is 20%, but we can basically improve the design and theoretically boost the efficiency up to a maximum of 50%. We can't make it better than 50% based on the temperatures that we're operating at. If you wish to improve the Carnot efficiency, one of the best ways to do that is to decrease TL, make it as low as possible, or increase TH, make it as high as possible. And so that will increase the maximum efficiency that can be obtained for a given heat engine. So either decrease TL or increase TH, and that will make the efficiency go up. 24. 2,000 joules of work is used to remove 6,000 joules of heat from the inside of a refrigerator. The operating temperatures of this device are 270 Kelvin and 305 Kelvin. How much heat energy is expelled into the environment? So go ahead, take a minute, and try this problem. Now, in the last example, we drew basically a heat engine that looks like this. We can also draw the refrigerator like this as well. So TH is 305 Kelvin, and TC, that's the low temperature, that's 270 Kelvin. In the last example, QH was basically the thermal energy produced by the engine, and this flowed in a downward direction. QC was the heat energy that was expelled into the environment, and the engine produced a certain amount of work. Now, for the refrigerator, the energy flow will be different. Instead of getting mechanical work out of the engine, for the refrigerator, we're going to put in mechanical work so as to pump heat energy from the inside of the refrigerator where it's cold and pump it all the way outside of the refrigerator, that is to the environment where it's warm. So that's the energy diagram that we're dealing with for the refrigerator. So let's focus on part A. How much heat energy is expelled into the environment? So we're looking for QH, the heat energy that is expelled outside of the refrigerator. Now we saw that W is the difference between QH and QL. Or QC. QL, QC, I might have mixed them up, but they're the same. I think in the last example I used QL, so let's stick with that. Now, if we add QL to both sides, then QH is going to be the sum of W plus QL. W is 2,000 joules. QL is 6,000. So QH is going to be 8,000. So that's the answer for part A. And we can see this in the diagram. So we have 6,000 joules of energy taken from the inside of the refrigerator, and we're putting in 2,000 joules of mechanical work, and we're expelling 8,000 joules of energy to the outside of the refrigerator. So that's it for part A. Part B. What is the coefficient of performance of this refrigerator? The coefficient of performance is QL divided by W. QL is 6,000 and W is 2,000. So canceling the zeros, we get 6 over 2, which is 3. So the coefficient of performance is 3. So that means that using 2,000 joules of mechanical work, we were able to pump 3 times that energy, or 6,000 joules of heat from the inside of the refrigerator into the environment. Let's say, for example, if the coefficient of performance was 5. This would mean that whatever amount of electrical work that we put into the refrigerator, we can pump 5 times that amount of heat from the inside of the refrigerator back out into the environment. So let's say if the work was 2,000 joules. If CP is 5, then QL will be 10,000 joules. So 10,000 joules will be taken from the inside of the refrigerator and pumped into the outside along with the 2,000 joules of mechanical work. So 12,000 joules of heat energy will be pumped outside of the refrigerator. It will be 10,000 plus 2,000. So the coefficient of performance is basically the ratio of the thermal energy that can be removed from the inside of the refrigerator in relation to the mechanical work of electrical energy that you're putting into the refrigerator to get the job done. Now let's move on to part C. Calculate the ideal coefficient of performance for this device. The ideal coefficient of performance is going to be TL divided by TH minus TL. So TL is 270, TH is 305. 305 minus 270 is 35. So 270 divided by 35, that's 7.7. So this is the maximum coefficient of performance that can be achieved for this particular device based on the operating temperatures. But based on the current values of energy that we're getting with this device, the current coefficient of performance is 3. But we can enhance the device and ideally get it close to 7.7. Number 25. A heat pump with a coefficient of performance of 4.0 uses 2,500 joules of work to pump heat from the environment at negative 10 degrees Celsius into a house at 25 degrees Celsius. How much heat energy is added to the house? So let's draw an energy diagram. So let's convert the temperatures from Celsius to Kelvin. Let's add 273 to those values. Negative 10 plus 273 is 263 Kelvin. And 25 plus 273 is 298 Kelvin. Now, the direction of energy flow for the heat pump is very similar to that of a refrigerator. We are going to use work in the form of electrical energy to pump heat from a cold environment, so this will be QL, into a warm environment, which will be QH. So this device is useful in the wintertime if you want to keep your house warm. Now, what is part A? How much heat energy is added to the house? What are we looking for? So we want to calculate QH. And we have W and CP. It turns out that the coefficient of performance for a heat pump is QH over W. So rearranging the equation, multiplying both sides by W, QH is the coefficient of performance times W. So that's 4.0 times 2,500 joules. So 4 times 25 is 100. So 4 times 2,500 is 10,000. So that's how much energy is going to this house. 10,000 joules of heat energy is being added to the house. Now, how much heat energy is removed from the environment? So we're looking for QL. Now we know that W is QH minus QL. So if we move QL to this side, it's going to become positive. If we move W to the other side, it will be negative. So QL is going to be QH minus W. So QH being 10,000 and W is 2,500. So QL is 7,500 joules. So that's how much heat energy is going to be taken from the outside of the house, that is from the environment, and pumped into the house. And we're putting in 2,500 joules of work to accomplish that. Now let's move on to part C. What is the ideal coefficient of performance for this heat pump? The coefficient of performance is QH over W, and W is QH minus QL. The ideal coefficient of performance is not based on Q, but it's based on T. So similar to what we see here, it's going to be TH over TH minus TL. In the last example, the coefficient of performance, the ideal coefficient of performance for a refrigerator was TL over TH minus TL. So note the difference between these two. So let's go ahead and finish this problem. So TH is 25 plus 273, that's 298 Kelvin. And TL is 263 Kelvin. 298 minus 263 is 35. And 298 divided by 35, that's going to be 8.5. So this is the maximum coefficient of performance that can be obtained for this particular heat pump based on the operating temperatures. And if we compare it to the actual value of 4.0, this value is not that bad relative to its maximum. Number 26, calculate the change in entropy that occurs when 50 grams of ice melts into liquid water. The latent heat of fusion for ice is 333 joules per gram. The formula that we need to calculate the change in entropy, which is represented by the symbol delta S, it's equal to Q, the heat absorbed, divided by T, which is the temperature in Kelvin. Now we can calculate Q using this equation. It's going to be the mass times the latent heat of fusion, since we're melting ice and we're not changing the temperature. So the mass of ice is 50 grams, and the latent heat of fusion for ice is 333 joules per gram. So what that means is that it takes 333 joules to melt 1 gram of ice. So to melt 50 grams of ice, it's just going to be 50 times 333. So the heat absorbed is positive 16,650 joules. So now we can calculate the change in entropy, delta S. So it's Q divided by the Kelvin temperature. Now, ice melts at 0 degrees Celsius, which is equal to 273 Kelvin. So dividing those two numbers gives us 60.99, which we can say that is approximately 61 joules per Kelvin. And this is positive. So that's how we can calculate the change in entropy that occurs when melting ice into liquid water. Number 27, estimate the change in entropy that occurs when 200 grams of water is heated from 20 degrees Celsius to 80 degrees Celsius. The specific heat capacity of water is 4186 joules per kilogram per Celsius. So let's begin. Let's start with this equation. Instead of Q equals ML, it's going to be Q equals MC delta T, because there is a temperature change involved in this problem. Now the mass of water is 200 grams, but the specific heat capacity has the unit kilograms. So we need to convert grams to kilograms. As we know, 1 kilogram is 1,000 grams. So it's 200 divided by 1,000, which is 0.2 kilograms. And then times the specific heat, which is 4186 joules per kilogram per Celsius. And then the change in temperature, that's 80 degrees Celsius minus 20 degrees Celsius. So we can cancel the unit kilograms and the unit Celsius. So it's 0.2 times 4186 times 80 minus 20, which is 60. So Q is going to be 50,232 joules. So now let's calculate delta S. Delta S is Q over T. So what value should we use as the Kelvin temperature? Because we have two different temperatures. Let's begin by converting the Celsius temperature to Kelvin. So we need to add 273. 20 plus 273 is 293. 80 plus 273, that's 353. So what we're going to do is we're going to use an average temperature. And so this is going to approximate the change in entropy. So let's add up these two numbers, and then let's divide it by 2. So 293 plus 353, that's 646 divided by 2, that's 323 Kelvin. So let's go ahead and divide those two numbers. So this is going to be positive 155.5 joules per Kelvin. So that's the change in entropy that occurs when 200 grams of water is heated from 20 degrees Celsius to 80 degrees Celsius. And so that's basically it for this video. That's all I got. Don't forget to subscribe if you really like this video. And thanks again for watching. Hopefully I'll see you in the next video.